Dear student friends, let us revise some basic things. First, we consider linear non-homogeneous delay differential equation of the form x dot of t equal to ax of t plus bx of t minus r plus function f of t. Okay, due to presence of this f of t, this becomes non-homogeneous. For this problem, with initial data x of t equal to phi of t, where t is in the interval minus r 0. For this problem, we discuss one bound mod of x of t is less than or equal to 1 plus mod b into r multiplied by norm phi plus integral from 0 to t mod of f of s ds into e raised to mod a plus mod b t. And if we put a equal to 1 plus mod b into r, small b equal to mod a plus mod b, then we can easily show that this is nothing but mod of x of t is less equal to a e raised to bt into norm phi plus integral mod f of s ds. Okay. Now we consider homogeneous problem x dot of t equal to ax of t plus bx of t minus r, and initial data is phi of t equal to 0 for t less than 0 means minus r less equal t less than 0, and it is 1 when t equal to 0. Okay. Now norm of phi is equal to 1 here. Okay. Norm phi means we have seen that it is supremum of all the values of phi on the interval minus r to 0. Okay. So here it is 1. Norm phi is 1. Further, f is 0. So in this case, we can see that the bound on solution is simply a e raised to bt. Okay, norm x of t is less equal a e raised to bt. Small a is 1 plus mod b r, and b is mod a plus mod b. We have seen the concept of fundamental solution. So for that we need characteristic equation. So what is characteristic equation for homogeneous problem? It is h of r equal to lambda. It should be h of lambda. Sorry. h of lambda equal to lambda minus a minus b e raised to minus r lambda. Okay. And fundamental solution of this problem is nothing but solution capital X of t such that Laplace transform of capital X of t is in variable lambda, it is 1 upon h of lambda. Okay. So the solution of this linear homogeneous problem with this initial data whose Laplace transform is 1 upon h of lambda is called fundamental solution. Okay. Now we can see that for this fundamental solution, we have two things. First thing is bound. Bound is norm of x of t is less equal a e raised to bt. Okay, so it is simple modification of this thing. Norm phi is 1 and f is 0. Okay, so a is 1 plus mod b r and b is small b is mod a plus mod b. So bounds are given in terms of coefficients. Okay, coefficients and delay term r. Second thing we studied is representation of x of t in terms of inverse Laplace transform. Okay, so if Laplace transform of x of t is this one, then x of t is given by using inverse Laplace transform. It is limit t tends to infinity 1 upon 2 pi I integral from say c minus it to c plus it. E raised to lambda t into 1 upon h of lambda d lambda. Okay. We use another notation for this integral. So that is, we have seen that x of t equal to this thing in short is denoted like this integral this c e raised to lambda t into 1 upon h of lambda d lambda. Okay, and here this c should be greater than b is this one. Okay, so this is true for any c satisfying this condition, c is greater than b. Okay, now our aim is to prove these two things in terms of characteristic roots. Okay, so characteristic roots means roots of h of lambda equal to 0. Okay, we already have seen that real part of characteristic roots is playing important role in deciding stability of solution. Okay, so real part things are important. We have seen that there are so many roots of h of lambda, but almost all the roots are lying on the left hand side of vertical axis. Okay, so our aim is to prove two things. First we define maximum of real part of all the roots of h of lambda. Okay, so we denote it by alpha 0. Okay, so maximum of real part of lambda such that h of lambda equal to 0. Okay, so what we do, we consider all the roots of h of lambda, form a set of real parts of all these roots and take maximum. Okay, such thing will exist because almost all roots lie on the left of vertical axis. Further, we have proved that there is certain value okay, such that no root will lie on the right hand side of that vertical line. Okay, this we already have seen. So such alpha 0 exists. Now what we do, we take alpha greater than alpha 0, and what we do, we show that first thing, x of t is given in terms of integral on this line passing through alpha. Okay, here it was line passing through C. Okay, so C minus IT to C plus IT, T tends to infinity means vertical line passing through C in complex plane. Okay, 1 upon 2 by I. Here it was inverse Laplace transform. This was the condition. Now we will show that if we take any alpha which is greater than this bound alpha 0, then x of t can be written as limit t tends to infinity 1 upon 2 pi I integral alpha minus it to alpha plus it e raised to lambda t into 1 upon h of lambda d lambda. Okay. Okay, so this is the change. Second thing, so we provide this in terms of maximum of real parts of roots of h of lambda. Second thing is about this such bound. We provide again bound in terms of these things. So we are going to prove another result which says that this x of t, that is fundamental solution, is bounded by k e raised to alpha t for some constant k. Okay. Okay, so earlier it was a e raised to bt. A and b are in terms of coefficients a, b and delay r. Here we are going to provide this bound in terms of this maximum of real part of lambda such that h of lambda equal to 0. Okay, so we prove these two results. Let us consider first lemma. If alpha 0 is maximum of real part of lambda such that h of lambda equal to 0, then For any alpha greater than alpha 0, x of t is given by this integral along the line passing through alpha e raised to lambda t into 1 upon h of lambda d lambda. Okay. Let us prove this result. We already have seen that x of t equal to, it is inverse Laplace transform of x, means it is given by this integral e raised to lambda t into 1 upon h of lambda d lambda along the vertical line passing through C, where C is sufficiently large real number. We may take C greater than alpha. Okay. If alpha is greater than C, then we readily get this result. Okay. Because this integral is true for any C greater than B. B is bound corresponding to that solution. Okay. We already have seen. Now, if alpha is greater than C, then it is clear that alpha is also greater than B, and this will hold automatically. Okay, nothing to prove. So we suppose that this alpha is smaller than C. Okay. In bracket, we may write otherwise the result holds automatically. Now we consider the rectangular region. Consider the rectangular region, say gamma, in complex plane. We call this as gamma. This point is C plus IT. We are in complex plane, so we call horizontal axis as real axis and vertical axis as imaginary axis. Okay, so this point is C plus IT. This is C minus IT. This point is alpha plus IT. and this corner is alpha minus it. This means on real axis, this point is nothing but alpha. Okay, alpha 0, we may say. This point is C. Okay, on imaginary axis, this is, okay, so I made a mistake. This should be capital T. So this point should be minus T. Okay, so this is not origin. Remember, this origin is somewhere here. This is minus T and this is T. Okay, so that this point is nothing but C comma minus T. This is C, T, this is alpha T, and this is alpha minus T. Okay, so these are four corners. Now we consider this as a directed rectangle. Okay, this is boundary of gamma. Okay, so directions are like this, anti-clockwise, okay, or positive. So we call this first vertical line as L1. This is M1. This is L2. And this is M2. Okay, so we consider these four line segments. Okay. So these form boundary of region gamma. Let L1, M1, L2, M2, that is nothing but del gamma. Del is symbol used to denote boundary of region. Okay, so this del gamma be the boundary of gamma in the direction indicated, that is anti-clockwise. So we may write equations of these lines using these 2 points. Okay. We have equations of these line segments. L1 equal to set of all points of the form C plus I tau. Tau is variable, C is fixed here. So tau is between minus capital T to plus capital T. Okay. L1 here, L1, every point on this line is of the form C plus I tau. Okay, so tau is from minus T to plus T. Okay, so minus T less equal tau less equal to. This is equation of L1. Similarly, we write equation of other line segments. L2 is alpha plus I tau such that minus T less equal tau less equal T. M1 is line segment given by sigma plus I capital T. Sigma is variable here. Sigma is between alpha and C. Alpha less equal sigma less equal C. Okay, so this is M1. Every point on this line is of the form alpha plus sorry, here capital T is fixed on this line. Okay, so sigma plus IT, and sigma is between these two numbers alpha and C. Okay, alpha less equal sigma less equal C. Okay, so this will provide all the points on the line M1. Similarly, M2. M2 is sigma minus IT. It should be sigma plus IT, same equation. Just a minute. Sorry, it should be sigma minus IT because minus T is fixed here. Okay, fine. It is sigma minus IT. So on this line, imaginary axis point is minus T, which is fixed. Real axis point is changing. Okay, on M2. So sigma minus IT, sigma is between alpha and C. Okay. So these are equations of these 4 line segments. Things are not difficult. Okay. Now we have one important observation. We have taken this alpha greater than alpha 0. Okay. If alpha is greater than alpha 0, then what is speciality of alpha 0? Alpha 0 is maximum of real part of lambda such that h of lambda is equal to 0. Means if we consider vertical line in complex plane passing through alpha 0, then all the roots of h of lambda lie on the left side of that vertical line. Okay, some roots may be on that vertical line. That's all. Okay, so this is because real of lambda means that vertical line. Okay, so in this plane, alpha is greater than alpha 0 means alpha 0 will be somewhere. Okay, so let me sketch. If my line is like this, vertical line means if I'm saying this is my alpha 0, then vertical line passing through this point alpha 0 comma 0 in complex plane, then all the roots of h of lambda lie on the left hand side of this line. Some roots may be on this line. Okay, so we have one guarantee that no root of h of lambda lie in this rectangular region gamma. Okay, so this gamma does not contain any root of h of lambda. Okay, so so this is purposefully selected rectangle. Okay, so we have h of lambda in the denominator. Okay, so denominator will not be 0. It is guaranteed that in this region, denominator of this function e raised to lambda t upon h of lambda will never 0. Okay, that means this function will be analytic. Okay, and if some function is analytic in this region, then by Cauchy-Gorsa theorem, integral along this boundary will be 0. Okay, so we are going to use that result. Since alpha is greater than alpha 0, all the roots of or zeros of, okay, h of lambda are on the left of the line x equal to alpha. Okay, so x equal to alpha means this vertical line. Okay, so that means h of lambda has no roots in the rectangular region gamma. That is h of lambda has no zeros or roots, okay, in the region gamma. Therefore, the function e raised to lambda t into 1 upon h of lambda is analytic in gamma. Okay, so this is analytic function. Therefore, by Cauchy-Borsa theorem, integral of e raised to lambda t into 1 upon h of lambda along the boundary of gamma, that is del gamma, is equal to 0. Okay, so we call this as 1. Now this means this integral along the boundary of gamma means integral along L1 plus integral along M1 plus integral along L2 plus integral along M2. Okay, so we split that integral in 4 these integrals. Okay, note that this integral along boundary of gamma is sum of 4 integrals, integral along L1 plus along M1 plus along L2 and along M2. We call this as 2. Now what is our claim? What we want to show? We will show that limit as t tends to infinity, integral along M1 e raised to lambda t into 1 upon h of lambda d lambda equal to 0. This limit is 0 and the same thing along M2 is also 0. So these two are our claims. Okay, so we are going to prove this. Once we prove this, then we may consider here limit as t tends to infinity. Of course, we can have 1 upon 2 pi I, which is constant. Okay, we can multiply this by 1 upon 2 pi I, take limit as t tends to infinity, and we use 1 and 2. So what we get? We get integral along L1 plus integral along L2 is 0. Okay, because this total is 0. Okay, further we are going to prove that along M1 and along M2 these are also 0 in the limit. So if we take limit, then integral along L1 plus integral along L2 is 0. But what is integral along L1? This is from c minus it to c plus it. We can multiply by 1 upon 2 pi I and taking limit as t tends to infinity. So it is nothing but this one. Okay, this thing. Limit as capital T tends to infinity 1 upon 2 pi I integral from c minus it to c plus it e raised to lambda t 1 upon h of lambda d lambda. Okay, so this is along this line L1. Okay, so this is same as this plus integral along L2 equal to 0. But what is integral along L2? It is from alpha plus it to alpha minus it. Okay, so that we can put minus sign and write it as from alpha minus it to alpha plus it. Okay, so it is nothing but minus this integral. Okay, so what we are going to show, this integral minus this integral equal to 0 means this is same as this, and this is what we want to prove. Okay, we want to prove this, we already have shown. So we have capital X of t equal to this integral, and we are going to show capital X of t can also be represented by using this integral in terms of alpha. Okay, so we will show that this integral is same as this one. Okay, so for this these two are important things. Okay, let us see. So first we choose t0 so that capital T greater equal to t0 implies square root of 1 plus alpha square by t square minus 1 upon t into mod A plus mod B e raised to minus alpha r is greater equal 1 by 2. Okay, so we can select capital T so that this holds. Okay, in this case capital A, capital B, R and alpha, all these are fixed things. Okay, so we are going to select capital T0 such that capital T greater equal T0 implies this holds. Okay, so we can always find such capital T. So we can adjust value of capital T accordingly. Okay. So we call this as 3. If T is greater equal T0 and lambda is on the line segment M1, means lambda is on M1 means lambda is of the form sigma plus I t, and sigma is between alpha and c. Alpha less equal sigma less equal c. Okay, so this is M1 line segment M1. Okay, here. Then what is mod of h of lambda? It is equal to mod of h of lambda. We know it is lambda minus a minus b e raised to minus lambda r. Okay, and now lambda is nothing but sigma plus it. Okay, so we may write this as sigma plus it minus a minus b e raised to minus lambda r, means minus sigma r minus I capital T into R. Okay. Now this is of the form mod of u minus v, and we can write this as greater equal mod u minus mod v. Okay, so this we can write greater equal mod of sigma plus it minus mod a minus mod b into mod of this, mod of e raised to minus sigma r minus itr. We know that mod of e raised to z. Okay, so if we write e raised to z, that is e raised to x plus iy, then mod of e raised to z is nothing but simply e raised to x. Okay, because e raised to iy, its modulus is 1. Okay, so this is nothing but e raised, simply it is e raised to minus sigma r. Okay, now mod of sigma plus it is nothing but square root sigma square plus t square minus mod a minus mod b e raised to minus sigma r. Okay, now what is the relation between sigma and alpha? Sigma is greater equal alpha. Okay, so this thing is greater equal square root alpha square plus t square. Okay, minus mod a minus mod b e raised to this sigma I can replace by alpha. I'm explaining. Okay, so minus alpha r. Okay, so here I'm explaining how we can replace this sigma by alpha. Okay, so maybe I will use different color. Here I am replacing by alpha. Okay, here also. First thing is clear why I'm writing alpha here, because sigma is greater equal alpha, but this is not that much straightforward. Let us see how we can write. Reason is like this. First thing is your alpha is less equal sigma, therefore e raised to alpha r should be less equal, r is positive. Okay, so no issue. E raised to alpha r is less equal e raised to sigma r. Okay, and therefore you must have e raised to minus alpha r greater equal e raised to minus sigma r. Okay, that means we are taking inverse of thing, 1 upon thing. Okay, so e raised to minus alpha r means 1 upon e raised to alpha r. Okay, so inequality will change in this case. Okay, and this implies if we can multiply this by minus sign, then again inequality will change. Okay, and we can multiply by any number, say positive number, say mod of b. Okay, so minus e raised to minus alpha r is less equal minus e raised to minus sigma r. Okay, and therefore minus mod b e raised to minus sigma r should be greater equal, okay, I am writing minus sigma, okay, greater equal minus mod b e raised to minus alpha r. Okay, so okay, so, though sigma is greater equal alpha, there are two things. First thing is here it is minus sign, and second thing here also minus sign. Okay, because of two minus signs we have similar thing, greater equal. Okay, so it is maintained. Okay, now what is this right hand side? We simplify right hand side. We take t common from right hand side. Okay, so right hand side equal to capital T into square root. This is, I'm taking t common from square root, so I should divide by t square. So in bracket it should be alpha square by t square plus 1. Okay, I'm writing it as 1 plus alpha square by t square. Okay, everything is under root minus 1 upon t into mod a. I'm taking minus sign outside, so mod a plus mod b e raised to minus alpha r. Okay, so why I'm writing like this? Because of this thing. Okay, so this thing is greater equal 1 by 2. Okay, so actually such conditions are obtained accordingly. That means conditions do not come first. Okay, so first such inequalities are obtained, and as per requirements conditions are put. Okay, and finally the statement is written. Okay, so usually proof of the result comes first and then statement comes. Okay, anyway, so by 3 this should be greater equal, this square bracket is greater equal 1 by 2, and here it is t, so greater equal t by 2. This is greater equal t by 2, this is by 3. Okay, so this is mod of h of lambda is greater equal t by 2. Therefore, what about 1 upon mod of h of lambda? It should be less equal 2 by t. Okay, this is important observation, and therefore what is absolute value of integral over m1 of this e raised to lambda t into 1 upon h of lambda? It is less equal integral over m1 e raised to lambda t, absolute value of e raised to lambda t into 1 upon mod of h of lambda d lambda, and this is less equal 1 upon mod of h of lambda is less equal 2 by t. Okay, so this is 2 by t, and this is integral over m1 of mod of e raised to lambda t. Again, what is lambda? uh, Lambda is sigma plus it. Okay, lambda is sigma plus it. Okay, so mod of e raised to lambda t is simply e raised to sigma t. D lambda. Okay, so this is nothing but 2 by t and sigma. What are bounds on sigma? Sigma is between alpha and c. Okay, so sigma is less equal c, so that we can write this as less equal thing. Okay, we can write this is less equal 2 by t. E raised to sigma t, bound on e raised to sigma t is e raised to ct, because sigma is less equal c. Okay, and this is integral along m1 t lambda. So what is that? M1 means line c plus it to c minus sorry, c plus it to alpha plus it, m1. Okay, alpha plus it and c plus it. Okay, so here c plus it minus alpha plus it, it is integral of 1 along this line, it is c plus it minus alpha plus it. So simply it is c minus alpha. Okay, and what happens to this as t tends to infinity? C fixed, alpha is fixed, so as t tends to infinity, this tends to 0. Okay, so this is what we wish to prove, that is limit as t tends to infinity, integral of this along m1 is 0. Okay, so second thing is similar. Okay, so we will not prove this second part. Okay, therefore limit as t tends to infinity, integral over the line m1 e raised to lambda t into 1 upon h of lambda d lambda is 0. Similarly, in the similar way we can prove. Okay, similarly limit as t tends to infinity, integral along m2 is also 0. Therefore by 1 and 2, as we discussed earlier, these two integrals are 0. We are taking limit as t tends to infinity, and of course we can multiply by 1 upon 2 pi I on both sides and use 1, that means this is 0. You can show that integral along L1 plus integral along L2 is 0. Limit as t tends to infinity, we may write 1 upon 2 pi I, doesn't matter. integral along L1 e raised to lambda t 1 upon h of lambda t lambda plus limit 1 upon 2 pi I integral along L2 e raised to lambda t into 1 upon h of lambda t lambda is 0. Okay. So this is nothing but what is meant by integral along L1? Let us see. Limit as t tends to infinity 1 upon 2 pi I along L1 means from c minus I t to c plus I t. Okay. Plus limit 1 upon 2 pi I. What is meant by integral along L2? L1 means c minus it to c plus it. Along L2 means alpha plus it to alpha minus it. Okay, limits are set so that we can put minus sign by interchanging limits. Okay, so this is important. Limits are lower limit is alpha plus it. So I show alpha plus it and upper is alpha minus it. T should be capital. Now we can interchange limits and put here minus sign. So first term is nothing but that integral along the vertical line C. Okay, so that is this along C e raised to lambda t into 1 upon h of lambda d lambda. This is minus sign integral along the line passing through alpha e raised to lambda t into 1 upon h of lambda equal to 0. Okay, but first thing is x of t. Therefore x of t equal to this along alpha okay. So this proves our result. Okay, this proves lemma. Okay, so this is our first target. Let us see the second result. Theorem. Conditions are same as previous result. If alpha 0 is maximum of real part of lambda such that h of lambda equal to 0, then for any alpha greater than alpha 0, there exists a constant k such that the fundamental solution x of t satisfies mod of x of t less equal k times e raised to alpha t. Okay, so we already have seen similar bound for fundamental solution. Okay, mod of x of t is less equal a e raised to b t, and those a and b were depending on delay r and coefficients capital A capital B in the homogeneous difference delay differential equation x dot of t equal to ax of t plus bx of t minus r. Okay, here the bound is in terms of this alpha. Okay, so alpha is greater than alpha 0, that is maximum of real part of lambda, such that h of lambda equal to 0. Okay, let us prove this result. So we are going to use previous lemma. By previous lemma, mod of x of t is equal to integral along this line passing through alpha. Okay, e raised to lambda t into 1 upon h of lambda d lambda. Okay, now we consider t naught as in previous lemma. Suppose t naught is chosen as in previous lemma. Let lambda be a point in complex plane given by alpha plus I t. Okay, so here it is alpha plus I t, and t be a number which is greater than or equal to t0. Okay, now consider a function. If g of lambda is 1 upon h of lambda minus 1 upon lambda minus alpha 0, then alpha 0 is here. Okay, appearing in the statement alpha 0. Then we consider bound on z. Okay, then mod of g of lambda is equal to mod of right hand side. Now what is h of lambda? H of lambda is lambda minus a minus b e raised to minus lambda r. Okay, so this is h of lambda minus 1 upon lambda minus alpha 0. Okay, we simplify right hand side. Okay, so this is equal to, so this is lambda minus alpha 0 minus lambda plus a plus b e raised to minus lambda numerator. Okay, so in the numerator lambda gets cancelled and we have a plus b e raised to minus lambda r, and this minus alpha 0 is there. Okay, denominator is this multiplied by this. We call this as h of lambda for simplicity, that's all. Okay, h of lambda, and this is lambda minus alpha 0. Okay, now 1 upon h of lambda. If capital T is greater equal T0, lambda is like this, then there is bound on h. We have seen that 1 upon h of lambda is 1 upon mod of h of lambda is less equal to by t. Okay, so this we are going to use. This is less equal 2 by t. We replace 1 upon mod of h of lambda by 2 by t. And here we write mod of numerator is less equal mod a plus mod b into mod of e raised to minus lambda r. Again, what is lambda? Alpha plus it. Okay, so it is e raised to minus alpha r. Plus mod of alpha 0. Okay, we can replace minus by plus. We are writing this thing is bigger than this denominator. This is the only term which is remaining, mod of lambda minus alpha 0. Okay, I should write reason here. 1 upon mod of h of lambda is less equal to by t. This we proved in previous result. Okay. We call this as 1. Now, about this lambda minus alpha 0. Now, lambda minus alpha 0, lambda is alpha plus it minus alpha 0. Now, what is the relation between alpha and alpha 0? Alpha is bigger than alpha 0. Okay, so I can write this as greater than, not greater than, what I should write? Let me take modulus so that I can have inequalities. Okay, therefore mod of lambda minus alpha 0 is equal to mod of alpha minus alpha 0 plus it. Now I can write this is greater equal mod of alpha minus alpha 0 plus mod of t. T is positive anyway. No, alpha is bigger than alpha 0, so this thing is greater than 0. Okay, so that I can write this thing is greater equal simply mod of it, and this is nothing but t. Okay, that's all. Okay, so mod of lambda minus alpha 0 is greater than or equal to t, or 1 upon mod of lambda minus alpha 0 is less equal 1 upon t. Okay, now I can replace 1 upon mod of lambda minus alpha 0 in 1 by 1 upon t. Okay, so therefore by 1 mod of g of t, left hand side is mod of g of lambda. Sorry. mod of 0 of lambda is less equal 2 by t, and this is also replaced by t. Okay, so 2 by t square into everything else is as it is. Mod a plus mod b e raised to minus alpha r plus mod alpha 0. Okay, so integral along this line passing through alpha, that means limit as t tends to infinity 1 upon 2 pi I integral from alpha minus it to alpha plus it mod of 0 of lambda t lambda should be finite. It cannot be this integral cannot be infinity. Okay, this is bounded because t square is in the denominator. Okay, and we are taking values of t larger and larger. Okay, so this thing is bounded, and therefore mod of integral of e raised to lambda t into 1 upon, sorry, e raised to lambda t into g of lambda along this alpha is less equal, we can take modulus inside, it will be mod of e raised to lambda t, and mod of e raised to lambda t is less equal e raised to alpha t as in earlier cases. Okay, so lambda is alpha plus I t, so this is e raised to alpha t, and here integral mod of c of lambda d lambda, and now this is bounded, so we can write this as less equal some constant k1 e raised to alpha t is there. Okay, so for this integral we write less equal k1. Okay, it is bounded. Further, okay, actually we are interested in the integral of the form e raised to lambda t into 1 upon h of lambda. Okay, but we split into steps. How we write e raised to lambda t upon h of lambda? We write e raised to lambda t into 1 upon h of lambda minus 1 upon lambda minus alpha 0 plus 1 upon lambda minus alpha 0. Okay, so we are adding and subtracting this term 1 upon lambda minus alpha 0. Okay, our aim is this one, e raised to lambda t into 1 upon h of lambda, but we write this as e raised to lambda t into 1 upon h of lambda minus 1 upon lambda minus alpha 0, and we are adding the same term. Okay, so first this thing is g of lambda, so we are writing here e raised to lambda t into g of lambda. Now we write about second term. Furthermore, mod of integral e raised to lambda t into 1 upon lambda minus alpha 0 d lambda. Okay, so we see bound on this thing also. So e raised to lambda t into 1 upon lambda minus alpha 0. This is less equal again we take modulus inside the integral, and for mod of e raised to lambda t, we write e raised to alpha t. Okay, and this integral 1 upon mod of lambda minus alpha 0 d lambda. Okay, now 1 upon mod of lambda minus alpha 0 is less equal 1 upon capital T. Okay, so this is less equal e raised to alpha t into this 1 upon capital T d lambda. Okay, again, this is bounded thing. Okay, in fact, it will be reaching to 0 because we are taking limit as t tends to infinity. So we can, of course, write this is less equal k2 e raised to alpha t for some constant k2. Here also I should mention for some constant k1. This is also for some constant k2. Of course, everywhere we are taking t to be positive. Okay, for some constant k2. And now our result is ready. We just have to add k1 and k2. That's all. Okay. Therefore, mod of x of t is this one, integral e raised to alpha t, e raised to lambda t into 1 upon h of lambda. We rewrite this as e raised to lambda t into 1 upon h of lambda minus 1 upon lambda minus alpha 0 plus 1 upon lambda minus alpha 0. Then we take absolute value. Okay, and just a minute, this should not be absolute value. Okay, this should be simply x of t. Taking absolute value on both sides and using basic results in complex analysis, we get this is less equal this e raised to lambda t g of lambda d lambda plus this integral e raised to lambda t into 1 upon lambda minus alpha g. That means it is less equal k1 plus k2 e raised to less equal k1 plus k2 e raised to alpha t. And this we can write as k e raised to alpha t, where t is of course positive and k is k1 plus k2. Okay, this proves the result. Thank you.